Thank you, Kelly, and all of you for joining us today for another installment of Webinar Wednesday. Today's topic, Psychrometrics Deconstructed, Part 1. Sorry, my mouse has... There we go. All right. My name is Dan Hani. I'm Director of High Performance HVAC Solutions for Veritech, an educator. In 2016, Veritech reached out to me to see if I'd be interested in being the company's educator. Since HVAC systems generate 40% of the carbon footprint of a building, there was and is growing demand for creating more efficient HVAC designs. To meet developing codes and market needs, I began my engineering sales efforts in 2008 with a goal to become a resource for high-performance HVAC system concepts, design strategies, and various products available to meet those goals. How my career path developed is somewhat unique, as my bachelor and master's degrees are in fine art sculpture. My career began in the industry, however, in 1985, working as an estimator of air distribution products and fans at Norman S. Wright Company Southwest. During the 90s, my responsibilities expanded into outside sales. When a sales position opened up for a new company called Air Specialty Products, I expressed interest and secured the role as ASP's first hired outside salesperson and immediately moved into the design, build, healthcare, and institutional markets. In 2008, ASP's engineering sales position opened up. I volunteered and was assigned the task. Since then, I have made it my personal goal to become a regional resource in high-performance HVAC designs. Veritech realized this direction, met their corporate vision as an HVAC system solution provider, and the rest is history. I've also had the good fortune, since being at Veritech, of working with some very fine PEs in the industry and writing educational articles on high-performance HVAC solutions, one of them being, the most recent one being published in December of 2022 on 100% outside air systems, passive radiant cooling and heating systems. So, Veritech Solutions. Who is Veritech, for some of you who may be new to the webinar series? Veritech is an integrated system solution provider for HVAC equipment and controls. We can provide an HVAC platform for the most simplest of structures, whether it be a strip mall package DX 3-ton unit on a roof, or an integrated system for a hospital, healthcare facility, data center, or etc. We have a expertise in all of the HVAC systems available in the industry today, and we're pleased to say we can address any of the high performance design concepts that are available and be a resource for those perhaps when a building comes up that's looking to go beyond the conventional design. And I think, in fact, I know we're going to be seeing strengthening of our codes, an advancement of our codes. The IECC 2021 code, for example, has already been embraced by the city of Scottsdale. We're going to find other municipalities following suit. That means, from an engineering standpoint, ASHRAE Standard 90.1 2019 will need to be involved. With these increasing standards, how we do HVAC is probably going to be changing. In fact, the Department of Energy issued a determination back in 2021 that Standard 90.1 2019 will be the energy standard for future municipalities to adopt in their code language. So change is coming, and I'm pleased to say that HVAC systems are available to have designs meet these growing and expanding requirements. Consequently, we felt it was necessary to allow high-performance designs to become more accessible, that we re-engage on the fundamentals of HVAC. Let us make sure we understand the fundamentals so we can see how there really hasn't been anything has changed with regard to heat transfer. And one of the important topics to understand. To do that is psychrometrics, hence the topic of today's presentation. So with that being said, let us go ahead and begin today's session. Today's agenda, we're going to again review, which I provided an introduction in our one of our health and buildings session, the first session of this year. We're going to look at the White House indoor air quality initiatives. We're going to look at how the White House is engaging in the IAQ indoor air quality discussion and how it's working with ASHRAE to understand what guidelines might be implemented for building standards and designs for the future to create better indoor air quality. The White House also launched its Clean Air in Buildings website, and we'll touch on that. We're going to look at the physical properties of heat transfer. We're going to look at terms and definitions. We're going to look at the properties of air, and then we're going to deconstruct the psychrometric chart altogether and then rebuild it to demonstrate the various processes that could be evaluated and referenced in calculating building loads and energy requirements through thermal energy requirements in a building. We're going to take one quick application of the psychrometric chart with the data that you'll be encountering today. I thought we would save session 2 next June for a more expanded version of the process portion of how to apply the psychrometric chart. So let's go ahead and begin. Let's review the White House indoor air quality initiatives. Again, as I mentioned in the previous session, on October 11th, the White House held its first IAQ summit. Its goal was to improve indoor air quality within buildings used every day as an essential part of the Biden administration's plan to manage COVID-19 in the fall and the winter. Remember, at that time, we were not sure how COVID-19 would behave as a pandemic. Fortunately, it turned out to be not as serious as it potentially could have been, and for that, we're grateful. However, it did bring the White House and the federal government into the indoor air quality discussion. So consequently, in order to expand the White House initiative to create a cleaner environment within buildings, they launched their Clean Air in Buildings Challenge. The Clean Air in Buildings Challenge is a call to action for organizational leaders and building owners and operators to assess their indoor air quality, make the necessary ventilation, air filtration, and other type of air cleaning improvements necessary to improve IAQ. The Clean Air in Buildings Challenge asks building owners who sign on to submit to 4 commitments. And I want to pay particular attention to commitment 2, which is being the optimization of fresh air ventilation. The Clean Air in Buildings Challenge is asking to bring clean outdoor air indoors and circulate when it is safe to do so. Why do I bring that into today's session on psychrometrics? If we see a proper increase of outside air, which we could see in the future, more ventilation rate, more outside air coming into buildings to create better IAQ. There are movements going on within ASHRAE, evaluations going on, and what that might mean. We have to understand psychrometrics to do that. So there are pressures occurring in our industry that invite us to re-engage and reacquaint ourselves with the fundamentals we are challenged with as HVAC professionals. Again, a reminder from a previous session that the CDC offers this advice that when indoors, ventilation mitigation strategies can help reduce viral particle concentration. And one of the recommendations the CDC submits is to eliminate HVAC air recirculation. The EPA acknowledges that inadequate ventilation can increase indoor pollutant levels by not bringing in enough outdoor air to dilute emissions from indoor sources. So an important approach to lowering the concentrations of indoor air pollutants is to increase the amount of outdoor air coming into a building. In presenting this, I've been challenged by audiences as to, well, does that make sense if you have a building in downtown Phoenix or in downtown Los Angeles? The EPA website offers a very expansive website on indoor air quality and indoor environmental quality. On the page, it lists the various contaminants we can encounter in a building, indoor air pollutants versus outdoor air pollutants. Now be aware, what's listed for outdoor air pollutants is a discrete list. It's acknowledged that there are more contaminants than the list the EPA is actively measuring and monitoring. However, the EPA does say that studies of human exposure to air pollutants indicate the indoor levels of pollutants may be 2 to 5 times or occasionally 100 times higher than outdoor levels. Let's just hope your building isn't like next to a manufacturing center that is dumping pollutants into the air close to your outside air intake. There's another dynamic moving within ASHRAE or occurring within ASHRAE. It's on evaluating CO2, carbon dioxide levels as a potential for being a pollutant. There was a wonderful article in the ASHRAE Journal, June 2022 edition called ASHRAE Position Document on Indoor CO2. It was written by Robert E. Stum, PE. Stum states in the article, of particular interest are several studies providing substantial evidence of acute exposure to CO2 at levels as low as 1,000 parts per million that induces significant reductions in cognition and decision-making abilities. So to reduce indoor CO2, it is necessary to increase a building's outside air, even in Los Angeles. Even though its levels have increased substantially, all but doubled since the mid-1980s, there is still almost half as much CO2 outdoors in downtown LA than there is in your average building. So CO2 is being evaluated, and stay tuned for that as we begin to bring that topic to the foreground. So let's re-engage on today's topic. Let's talk about the physical properties of heat transfer. Again, what is the purpose of a heating and ventilating system? It is to provide personal thermal comfort and to create an environment with superior indoor air quality. To maintain building thermal comfort, however, occupants must feel neither too hot nor too cold. So consequently, any energy or thermal gain that occurs in a building during our warmer times of year has to be removed from a space. To maintain a comfortable environment, energy needs to be transferred. All of that accumulating energy needs to be moved from the building to outdoors in summer, and in winter, added to a building. Thermal energy needs to be added to a building when the cold outdoor ambient condition absorbs and robs the building of the heat energy that might build up inside of it. So what is heat transfer? Well, according to Britannica, it is defined as any or all several types of phenomena that convey energy and entropy from one location to another. So HVAC systems cool a building when that system absorbs the energy gained in that building when we're in cooling mode and transports it to outdoors, or during the winter seasons, adding energy to a building to compensate for the energy lost to the outdoors during our colder times of year. So the question is, well, that's fine. How much energy? How much heat needs to be moved? Well, you need to calculate the amount of building energy or total load gained or lost, and the amount to be moved to maintain constant design temperature. If you have energy gain in a building and you're trying to maintain a thermostat, that energy gained has to be moved out so that we maintain constant design conditions. So how do you calculate the amount of energy to be moved, whether it be in cooling or in heating? The psychrometric chart references the energy or enthalpy amount to be moved to maintain space design conditions. Well, I thought you'd find it of interest in just having a little interlude before we dive into the spaghetti of psychrometric charts. There's a fun article written in the ASHRAE journal in November of 2004 on the history of the psychrometric chart. Psychrometrics goes back to the mid-19th century. There's work done by a scientist by the name of James Glasher, who established the hygrometrical tables. They were the first reliable tables that demonstrated the relationship between water vapor pressure, barometric pressure, wet bulb, dry bulb, and other air property conditions. Those tables were expanded upon by the American meteorologist William Farrow in 1886. They were expanded even further in 1900 by a Professor Charles Marvin, and it was Richard Mollier at the turn of the century around 1900 who created the first Mollier diagrams illustrating the relationship between moist air and enthalpy. The psychrometric table as we know it today, however, was invented by Willis Carrier. In response to an air quality problem Carrier encountered at the Willems Lithography and Publishing Company in Brooklyn, Carrier submitted drawings for what became recognized as the world's first modern air conditioning system. By 1903, he completed the world's first scientifically based air conditioning system specifically designed to control humidity. In 1904, Carrier generated the psychrometric table to simplify the task of air conditioning design and graphed all of the Marvin's tables onto a sheet that we have come to know today. This resulted in the basic psychrometric chart. So that was effectively the birth of air conditioning as we know it today. The psychrometric chart is HVAC. It is heat transfer, and to know it and to be fluent with it is necessary to understand the properties of air. Before we begin to explore the psychrometric chart, let's make sure that we understand the fundamental terms. And yes, these terms are repeated from previous sessions because it's so easy, at least for me, to lose context of terms unless we just have them continually brought back into our memory. So let's look at the term change. What is the term change? It's to make different in some particular, to alter, to bring about a change in state. So what is force? Force in mechanics is any action that tends to maintain or alter the motion of a body or to distort it. And I would say even a body to move energy as well. So you need a force to move energy. What is pressure? Pressure is a continuous physical force exerted on or against an object by something in contact with it. We covered pressure and we mentioned that where there's an imbalance of a high moisture state with a low moisture state or a high humidity situation adjacent to a low humidity condition, then we will have a transfer of moisture from wet to dry due to vapor pressure. Energy, we need to make sure we understand the term energy. Energy in physics is the capacity for doing work. There are many different types of energy. There's potential, kinetic, thermal, electrical, chemical, etc. We're focusing on thermal energy today. All forms of energy are forces associated with motion or the moving of energy. So energy is directly or indirectly the agent for motion, quantitative or qualitative change. Energy is a force, and energy is required to move heat or thermal energy mechanically. Thermal energy is measured in temperature. Temperature is the value assigned to the amount of thermal energy present in a sample of air. Thermal energy equals sensible heat, or temperature in dry bulb. It is a measure of the rate of molecular rate of molecular motion of a sample of air, how fast the molecules are moving. And we can assign a value to that energy present, creating that movement as temperature. So the higher the molecular energy, the higher the kinetic energy, the higher the temperature in the air that you actually feel. Well, what about water and heat energy? What about energy in the states of water? The amount of energy present to a sample of water determines the state it is in. If you remove energy from a sample of water as a fluid to a 32 degree, to a point where its temperature is 32 degrees, it will solidify. It'll become a solid. It'll undergo a change of state. If you add enough energy to a sample of water, it will evaporate. It will boil. Where liquid becomes a gas, and you have a heat of vaporization effect occurring. Condensation occurs when water vapor as a gas becomes a liquid. It's called dew point, when water condenses from a vapor into a liquid. ASHRAE standard 55% of the air, and it's relative humidity. However, as I mentioned in the humidity webinar Wednesday session last month, there is an absolute value for measuring the amount of water content in the air. Two ways of doing that, actually there are three, but I'm only listing two here, are dew point and specific humidity. Specific humidity measures the grains of water in a pound of air. So in order for water to stay in a gaseous state, in order for it to be vaporized, it requires energy. And that energy is known as latent energy. We can't feel it as temperature as we can dry bulb or sensible heat, but it is necessary in a sample of air to keep water in a gaseous state. It is latent energy. So what is latent cooling? It is removing enough thermal energy so water vapor cannot remain in a gaseous state anymore. It condenses out into a liquid at cooling coils, and that is how we control humidity. So all of HVAC involves an energy function. If you want to control thermal comfort with regard to temperature measured at a thermostat, you got to move energy. If you want to control humidity, the amount of water in a sample of air, you have to move energy. You have to rob from that sample of air the energy necessary to allow water to transition into a liquid state from a gaseous state. Let's look at thermodynamics. What is thermodynamics? Britannica offers this definition as the study of the relations between heat, work, temperature, and energy. What is enthalpy, a term we're going to be using regularly today? Enthalpy is an air sample's total energy. It is the total energy as the sum of the sensible and the latent energy in a sample of air at a given pressure and volume. So what is psychrometrics? Psychrometrics is the study of the thermodynamic properties of air vapor mixtures, partial pressures, and enthalpy. Just as an aside, where does the term psychrometrics come from? It's an adaptation of Greek words, suchron, meaning cold, and metron, meaning measurement. So just a little bit of trivia. So let's move into psychrometrics and the properties of air. So since we're in the business of heat transfer, moving energy from or to a building, depending on whether or not you're in cooling or heating mode, we have to provide heat transfer in controlled amounts of energy. It has to be determined the amount of energy to be moved to maintain building temperature set points. So in cooling, we have to calculate the total load, which is the sensible energy plus the latent energy. So to calculate that total load, we have to have an understanding, an implicit understanding of the terms and definitions that are of fundamental importance. And this is a repeat from our last session. We have to understand dry bulb temperature. Dry bulb temperature is the amount of energy in the space as measured by a room thermostat or dry thermometer. It is also called the sensible temperature, the heat that you feel in the air when you're feeling warm, or cold when there's an absence of energy in the air. Relative humidity, we have to understand relative humidity. The definition of RH is the moisture content in a sample of air as a percent of the total amount of moisture air can hold when it is fully saturated at a dry bulb temperature. So relative humidity is associated to temperature. It is relative to temperature. What is wet bulb temperature? Wet bulb temperature is a little more difficult, excuse me, because it's not intuitive. Wet bulb temperature is the lowest temperature air is cooled to by water evaporating into a vapor at a constant pressure. You measure room wet bulb temperature using a sling psychrometer, which is a dual thermometer device with a rotating handle on it. One of the thermometers has a moistened wet wick around the bulb and the other is left open. If you twirl that psychrometer in the air and allow for evaporation to occur at the wetted wick, energy is removed from the air around the wick in order to create the phase change of water in the wick into a gaseous state, because the evaporation process takes heat energy to create the state change. So the temperature, the wet bulb temperature generated measures the amount of energy robbed to create the change of state from water into vapor at that thermometer. And the dry bulb temperature measures the thermal energy. Consequently, you get dual readings, the dry bulb temperature and wet bulb temperature. The lower the wet bulb temperature, the drier the air, the more evaporation occurs from the wetted wick. The higher the wet bulb temperature, the more humid the air, and the rate of evaporation is reduced because of the high moisture content in the air in which the sling psychrometer was measuring. Dew point. What is dew point? Dew point is the temperature at which insufficient energy is present to maintain water in a vapor state and thereby condenses and becomes a liquid. So the higher the dew point, the greater the moisture content and humidity in a sample of air. The lower the dew point, lesser moisture content and humidity. Another term we have to understand to evaluate and apply the psychrometric chart is specific humidity, otherwise known as humidity ratio. It is the mass of water vapor in a sample of air measured in grains. There are 7,000 grains of moisture per 1 pound of water vapor. So that is a very important measurement because it measures absolutely what the content of water is in a sample of air, and it is not relative to temperature. Another term, again, that we need to look at is the term enthalpy, also associated with total load of a building. Again, the total load is the sensible and the latent load of a sample of air added together. It is measured in British thermal units, which is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. And just as an aside, there are 12,000 BTUs in 1 ton of load. So a 4-ton package DX unit has a nominal capacity of 48,000 BTUs. So the psychrometric chart, what is its purpose? The psychrometric chart's purpose, as decided and defined by Willis Carrier, is to be a reference sheet. It references the relationship between sensible energy, otherwise known as temperature, latent energy, known as humidity, and enthalpy, the total energy. The psychrometric chart, simply put, is a reference chart or graph. So to use and apply the chart, you can know any two air property values. And by knowing any two values, you can determine what the other values are. If you know the dry bulb and wet bulb, you can determine the relative humidity. You can determine the specific humidity. You can determine the absolute humidity. You can determine the vapor pressure, the cubic volume of air can be at those design conditions. All of these points are found on Willis Carrier's referential chart, the psychrometric chart. So the chart illustrates total process load of a system, the total heat energy to be transferred from a building in order to maintain building design conditions. So with that being said, let's delve into the psychrometric chart. Let's pull it apart into its component features. Before we begin that, I thought we would use as an example a more stringent building design guideline, ASHRAE Standard 170, to give us a design condition that needs to be met 24/7. In most of our commercial buildings and institutional buildings, we are only challenged with high humidity during our monsoon season. But because of the air requirements in many healthcare applications, their humidity conditions and controlling to them are a little more aggressive in a healthcare design standard such as ASHRAE 170. So we're going to start with that as a baseline for our evaluation of the chart. ASHRAE Standard 170 shows that a patient room needs to be maintained between 70 to 75 degrees dry bulb and not to max 60% relative humidity. So I thought we would look at two healthcare conditions used for patient room designs and even operating room designs, though I'm fully aware operating rooms today are being challenged now with low dry bulb temperatures of 70 degrees, 68 degrees, even as low as 65 degrees, which is causing some serious challenges for condensation and humidity issues in ORs that have to be addressed. So we're going to use this as our sample for evaluating the psychrometric chart. We're going to use 72 degrees dry bulb at 40% RH. We're going to look at our process evaluation, an outdoor air condition of 97 degrees dry bulb, 76 degrees wet bulb. Notice that it's not 115 degrees because the total enthalpy available in 97, 76 degree air with higher humidity is greater than an air condition of 115 degrees at 72 degree wet bulb. So we're going to take the more stringent case of a monsoon design day. So let's look at the psychrometric chart and let's take a sample of air from a hospital environment. Be aware that if you look at the psychrometric chart, I have listed 1,100 foot elevation. Well, that is because elevation impacts the properties of air. The properties of air at sea level are different from the properties of air at 5,000 feet, 7,000 feet, etc., because air is not as dense. So it's very important that when you apply the psychrometric chart, you apply it for the appropriate elevation the project's going to be situated at. We're going to look at the room condition of 72 degrees dry bulb, 40 degrees % RH. Well, looking at our psychrometric chart, let's orient ourselves with how the lines are situated. The x-axis of the psychrometric chart found along the bottom references dry bulb temperatures, and the range varies depending on the manufacturer of the chart. They can begin at 32 degrees and end at 115, 120. They can vary. The y-axis references dew point. You find your dew point along the y-axis. You can also find dew point along the saturation curve, and we'll explain why shortly. The y-axis also has a parallel line that to the dew point line that gives the humidity ratio or specific humidity, which gives a value of grains per pound of air. The y-axis also has the absolute humidity line, which is parallel to dew point and humidity ratio, and that measures the amount of the pounds of water in a sample of air. The parabolic lines, the semi-hyperbolic lines that span from lower left to upper right, are your relative humidity lines. And the furthest left parabolic line is your saturation curve, or 100% humidity. And the top right to lower left diagonal line is the enthalpy line that lists the BTUs of energy present within a given sample of air. So let's look at dry bulb. Let's look at the dry bulb temperature lines. Let's strip away all of the other lines to make it easier for us to visualize how dry bulb lines are followed. Again, the values for dry bulb begin along the x-axis, and they are to follow upwards in straight parallel lines for every temperature increment. So as you move from lower temperature to higher temperature, these dry bulb lines are shown there very clearly. So if we have a condition of 72 degrees dry bulb temperature, we can plot that on the psychrometric chart at 72 degrees and draw a line through that state point parallel to the other dry bulb lines. And this other little chart gives you a reference on the full psychrometric chart to get a better visualization of its location. Relative humidity. Again, relative humidity is an air sample's actual moisture content as a percentage in relation to the amount of moisture air can hold when saturated at a given temperature, 100% RH. Well, the relative humidity line is a semi-parabolic line that spans from lower left and extends to the upper right and expands through all of the increments. And it's shown in 10% level increments, 10, 20, 30%. So if you know that where the humidity lines are, you can now determine the 100% RH saturation curve, which is the curve at which an air sample can no longer hold water in a gaseous state and water vapor condenses into a liquid. So if we know our two state points, we know that we have an air sample at 72 degrees and 40% RH, we can plot a state point on the psychrometric chart where the dry bulb temperature intersects with the relative humidity line. That point of intersection is a state point on the psychrometric chart. So keep that point in reference to the saturation curve as I mentioned earlier. So what about wet bulb temperature? How do we plot wet bulb temperature? Again, we define the wet bulb temperature as the temperature measured at a thermometer with a wetted wick, and its evaporation rate and the amount of temperature impact depends on the humidity content of the air in which the value is being read. So we understand that our wet bulb temperature is along the values for the wet bulb temperature are to be found along the saturation curve. The lines of wet bulb temperature run from upper left to lower right in parallel order. So if we look at our state condition of 72 degrees, 40% RH, we calculate the actual, we plot our dry bulb temperature line, we find the state point intersection with the relative humidity line, and then once we have our state point, we draw the wet bulb line parallel to the wet bulb lines illustrated on the chart, and where that line intersects the wet bulb saturation curve, we can read the wet bulb value on that curve at 57 degrees. That's how you find your wet bulb temperature. It works the opposite way as well. If you're looking at an equipment schedule that shows dry bulb and wet bulb temperature, and you do if you have coils, that's for sure, but you don't know the relative humidity of the sample of air, knowing the wet bulb temperature and the dry bulb temperature and where they intersect will give you the relative humidity of that sample of air at those two temperatures. What about dew point? Dew point is the temperature at which there's insufficient energy in a sample of air to keep water in a gaseous state so it condenses into a liquid. Again, dew point is an absolute measure of moisture content in the air. Well, dew point lines run parallel to the x-axis, and they run in increments defined by the dew point level on the right hand of the chart or along the saturation curve, and we'll illustrate that momentarily. So let's plot the dew point using the psychrometric chart. Let's use our sample of air at 72 degrees dry bulb, 40% RH, which calculates out to a dew point of 46.4 degrees. So let's find our dry bulb line. Let's create our state point where the dry bulb line intersects the relative humidity line. And then we draw a parallel line through the state point to the dew point temperature value diagram on the right. And where that dew point line intersects that point on either side is your dew point, 46 degrees. So that's how you use the psychrometric chart to determine dew point. And this is going to become more and more important. ASHRAE standard 62.1 2019 has made a shift. They are no longer going to be referencing relative humidity, but dew point. And that will remove a lot of confusion in the industry for those who associate water content with relative humidity, because it is not uncommon for one to think that you can dehumidify an air by reducing the relative humidity in a space by increasing the space temperature. Well, it's true, the RH value will decrease, but the amount of water in the sample of air does not decrease. So moving to a dew point standard, I think, will bring clarity for more effective dew point humidity control designs in a building. So let's put it all together. Let's look at how we can use dry bulb and wet bulb to calculate the dew point. Let's look at our dew point line. Let's look at our state point, and let's look at where the dew point line intersects the saturation curve. Where that dew point line intersects the value along the saturation curve, that is your dew point temperature. And notice that whenever the dry bulb temperature and the wet bulb temperature are equal, that is your dew point. That's when air is at 100% saturation. There's not enough energy in air at that condition to keep water in a vapor state. It condenses into a liquid in the form of rain or dew. Specific humidity. Like dew point, specific humidity lines run parallel to the x-axis in assigned increments along the with an associated value along the y-axis. So again, specific humidity or humidity ratio is a measure of the amount of grains of moisture in a pound of air. And there's 7,000 grains in 1 pound of water. So let's look at our state point. Let's plot our curve. Let's determine what our specific humidity is. Let's look at our dry bulb temperature of 72 degrees. Find the point where it intersects with the relative humidity line to create a state point. Then we draw a line parallel to the x-axis through the state point to determine what the specific humidity is, how many grains of moisture are in a pound of air at 72 degrees, 40% relative humidity. What about energy? The whole point of this discussion, the whole point of HVAC. Remember when I said that all of HVAC has to do with moving energy? Well, we can assign energy values to states of air using the psychrometric chart. Let's look at our condition of 72 degrees, 40% RH, and then let's draw a line through the state point parallel to the values displayed on the enthalpy chart and graph. Where that line intersects the state point, we have an enthalpy reading. In this case, 24.89 BTUs in a sample of air at 72 degrees dry bulb at 40% RH. That's how many BTUs, that's how much energy there is in a sample of air at that condition. So we can reference the energy present in a sample of air using the psychrometric chart. Well, let's expand upon this now that we've identified all of the state points that are used, well, most of them anyway, in a psychrometric chart. Let's look at the process types. There's sensible heating, where we have an increase of dry bulb temperature. We follow an arrow along a line that's parallel to the x-axis in the amount of temperature change we see by adding thermal energy to a sample of air. We have sensible cooling. That's where we actually remove energy from a sample of air, causing a reduction of temperature. We have humidification. Look at the chart where we have and maintain the same temperature value, and we add moisture to a sample of air. We add grains of moisture to a sample of air. That is a process that drives upward on the psychrometric chart. We have dehumidification, which results when you remove water from a sample of air, and we have a reduction in the amount of grains of moisture in a sample of air, as well as consequently dew point. There's the process of evaporation, where we have water liquid evaporating into water gas. To make the state change from liquid to gas, energy is needed. That energy is robbed from the local environment, the atmosphere, causing a cooling effect as water becomes a vapor and turns into a gas. You have chemical dehumidification or desiccant dehumidification, where you have the reverse to evaporation occurring, where you actually reduce the humidity content in a sample of air by increasing the temperature in that sample of air, because as you remove the latent energy to keep water vapor as a gas, that energy now becomes thermal energy when that water is removed. You have heating humidification, as you would see in a steam humidifier in healthcare facilities, perhaps, or in institutions, where you have an increase of temperature, of dry bulb temperature, as well as an increase of water content, of moisture content in a sample of air. And you have cooling dehumidification, which is the process that occurs at a cooling coil, where you actually cool a sample of air, bring it to dew point, allowing that latent energy to be removed, allowing condensation to occur, thereby removing the amount of moisture content in that sample of air. These are the 8 processes, so let's evaluate them one at a time. Let's look at sensible heating. Let's look at if we take our sample of air at 72 degrees, 40% RH, and we heat it to 81 degrees, 30% RH. Well, if we look at the psychrometric chart, we are traveling left to right in our dry bulb temperature. Notice how the specific humidity and dew point did not change because we did not see a change in the content of water in that sample of air. Let's push it now to 95 degrees and 19% relative humidity. Again, we see no change in the moisture content. So the total heat gain in that sample, total temperature increase, is measured along the x-axis, which gives you the amount of degrees temperature of energy that was increased, that was included in that process. Notice that the specific humidity and dew point lines don't change. They remain horizontal. We do not see any change in moisture content for that sample of air. Well, to go from 72 degrees, 40% RH to 95 degrees, 19% RH, there is an increase of energy in that sample of air. So as temperature increases, relative humidity decreases, dew point remains constant. So the mass of water in grains remains constant because we're only adjusting the thermal energy. We're only adding thermal energy to a sample of air. Let's look at sensible cooling. This is an air conditioning unit. We start from our state point at 72 degrees, 40% RH. If we go to cool it now to 65 degrees, 51% RH, we notice we have no change in humidity. If we change it to 55 degrees, 73% RH, we still have the same amount of moisture in that sample of air. Right the way down to 46 degrees dry bulb, 100% RH, where dry bulb, wet bulb, and dew point are equal. In actual fact, in the process, and we'll demonstrate it shortly, it's not a linear reduction in temperature. You start seeing dehumidification as you closely approximate the saturation curve. It's not an abrupt change right at that saturation condition, and we'll illustrate that shortly. So if we look at the process, we notice that the dew point and specific humidity remain constant, temperature decreases. We have at the point of intersection between the temperature with the saturation curve, dew point and condensation, dew point is reached and condensation occurs, and we can illustrate the amount of energy that needs to be removed to create this change of state within that sample of air. So when we're cooling, temperature decreases, relative humidity increases, dew point remains constant, there's an overall energy decrease. Let's look at humidification. Let's look at 72 degrees, 40% RH. Let's start at our 72 degree point. Let's stay at 72 degrees and just increase the moisture content. By doing that, by increasing our RH at 72 degrees to 58%, your dew point increases and the grains of moisture increase. If you add more moisture, increasing humidity to 82%, the dew point increases even more, as well as our specific humidity. So if we look at that change and we look at the temperature, we're maintaining a constant temperature. The dew point increases, there's more moisture added to the air. Consequently, look at the increase of energy. So when you have a humidification process, moisture grains increase, relative humidity increases, dew point increases, but depending if temperature can remain the same. So that gives you an idea of the value of latent energy. even though you don't see an increase of space temperature, you do see an increase of energy because of the energy present to keep water in a gaseous state within that sample of air. Let's look at dehumidification. Now we're removing moisture from a sample of air. We're moving from 40% RH at 72 degrees to 27% RH. Dew point decreases. Specific humidity decreases. Let's take it down even further. That is the process. While maintaining a constant temperature at 72 degrees, we see a reduction of dew point of roughly 25 degrees. Temperature remains the same, dew point decreases, and the energy present in that sample of air decreases. It's been removed during the dehumidification process, and consequently, there is a reduction of energy even though the temperature remains the same. What about evaporation? I used to live our first home. We only had evaporative cooling. Quite frankly, I loved it. A little bit of a roof shaker on a little 1,200 square foot house. Well, let's look at the evaporation process for an evap cooler. Let's start with our sample of air at 72 degrees, 40% RH. As water evaporates, as that liquid water evaporates into a gas, in order to create a phase change from liquid to gas, energy is robbed, thermal energy is robbed from the sample of air to allow water liquid to become water vapor. So we see a reduction in dry bulb, but an increase of moisture content. Dew point is increased to 53 degrees, grains up to 62 by moving towards this 63-degree dry bulb condition during the evaporation process. So the direction of evaporation along the psychrometric chart is from lower right to upper left. You have an increase of dew point, the amount of water vapor added to a sample of air. Temperature decreases. Consequently, you have no energy increase. You rob Peter to pay Paul in a perfect exchange. Not any exchange is perfect. There's always an imbalance in one direction to another. But as a hypothetical, this is certainly the case. And why is that? Well, as latent energy increases, sensible energy decreases at a rate where you have a linear rate of change, and consequently, no energy change. What about chemical dehumidification, desiccant dehumidification? An excellent solution for controlling humidity in applications, especially for critical applications. Well, as we reduce moisture from the air, we actually give heat off into the ambient air condition because latent energy is now converted into thermal energy. Water vapor condenses into water liquid. So as the air gives up its latent energy, you have to have an increase in thermal energy. So if you notice, we have an increase in the set state point number 2 of 82 degrees. Temperature increases, dew point decreases. Again, no change of energy in a perfect exchange because the latent energy decreases at the rate that the sensible energy increases. So we have no energy change in that perfect transition. What about heating humidification, where we have 72-degree air at 40% RH and we heat it using a steam humidifier to 85 degrees, 40% RH. Notice how our RH value is the same, but our temperature varies. As our RH value is the same, however, our dew point increases and our specific humidity increases. So this is important as to why, an understanding why relative humidity values are temperature dependent. So if we look at the exchange using heating humidification, heating a sample of air using a steam humidifier in an air handler, we notice that we have an increase of dew point, we have an increase of thermal temperature, and consequently the sample of air increases in total energy. And last but not least, cooling dehumidification, a process we all hope will be working most effectively as we approach this summer season in Maricopa County. Let's look at 72 degrees, 40% RH state point. Let's look at cooling the air and reducing the humidity. Notice how that you have a reduction in relative humidity in relation to temperature. You have a reduction in dew point, a reduction of moisture in the grains. You have a cooling dehumidification process from upper right to lower left on the chart. Temperature decreases, dew point decreases, energy in that sample of air at a condensing cooling coil is decreases. Sorry, this is an error on my PowerPoint. This is the first time I've given this expanded version of the presentation. You will see a reduction in total energy, and this needs to be amended. So let's look at a process of air conditioning. Let's look at an office building. Let's look at an office building on a monsoon day with an air handler that has 10,000, that is providing 10,000 CFM of supply air, 2,000 CFM of outdoor air at our monsoon design condition of 97 degrees dry bulb, 76 degrees wet bulb. We have a room air condition of 75 degrees dry bulb, 50% relative humidity. At this ratio of the two airflows, the mixed air condition at the cooling coil is 76 degrees dry bulb, 61 degrees wet bulb. That is the condition of air that needs to be seen to at the cooling coil. So as that air passes through a chilled coil, the first thing we see is a reduction in the dry bulb temperature as thermal energy is removed. And then as you approximate the saturation curve, you see a process of dehumidification beginning to occur as you approach the saturation curve, and it accelerates rapidly at the point where it's closest to the saturation curve. I used a sample of 55 degree dry bulb, 54 degree wet bulb as a supply air condition off the cooling coil, a very common design condition that we see in Phoenix, Arizona. So looking at that change, or that process, the total energy removed is 8 BTUs per 1 pound of air. So consequently, you can calculate how many pounds of air are in 10,000 CFM. It's very easy. You can calculate the total load of heat transfer necessary to make that transition, the amount of energy that needs to be removed from a building in BTUs as calculated on the psychrometric chart, so all the space conditions remain at their assigned condition, 75 degrees on a thermostat, 50% RH in a building. What if you have a shoulder season and you need cooling on the interior and heating on a perimeter zone, especially in the early mornings? Well, here's where the energy problem manifests itself. Let's look at the overall enthalpy differential that has to occur. You have to dehumidify the air by bringing it close to the saturation curve. And then for the areas that need reheating, you need to reheat that sample of air back up to maintain a leaving air condition of 80 to 85 degrees. You regain all of the energy you just spent to remove to control the humidity. And this is why reheat systems are so inefficient. In fact, reheat in a hospital is responsible for a large proportion of energy consumption in the building. I used to know the value of it. I could be wrong. I think it's 70 to 80% in a hospital is devoted to just sheer reheat. it's putting energy back into a system after removing it to control humidity. So this is an important concept to understand as you begin to look at high performance HVAC systems. So let's look at an application of the psychrometric chart as we approach the end of this presentation. And I'm very sorry that we have gone over, but we're almost to the end here. What if we have a hospital lobby during the monsoon that is having a problem with diffusers condensing? Well, why is that? Well, hospital doors open and close throughout the day. Moisture from outdoors due to vapor pressure rushes indoors every time that door is open. Consequently, we lose control of humidity in the space. So how do we solve the problem? Well, we ask ourselves the question, when does condensation occur? Condensation occurs at a diffuser or any other surface when a surface temperature falls below space dew point. Think of a glass of iced tea during a summer day. So if you look at the psychrometric chart and you look at the state point of 75 degrees, 50% RH, and you draw the dew point line, you will find that the dew point of air at 75 degrees, 50% RH is 55 degrees. Well, if you're supplying 55-degree air to your diffusers and the surface temperature of your diffusers at 55 degrees, condensation occurs. That's just all there is to it. So by identifying the dew point in your space in a room that has condensing occurring on diffusers or windows, you can then look at, certainly for a VAV system with reheat capability, of bumping your leaving air condition off the VAV box 3 degrees above space dew point, that your humidity or your condensation issue in that application should go away. So Psychrometrics Deconstructed, just a quick review. We've covered a lot of ground, and again, this presentation will be available at Veritech's website. We covered the White House indoor air quality initiatives. We demonstrated that there's a movement occurring today that's looking at increasing ventilation rates. We looked at the physical properties of heat transfer, a history of the psychrometric chart. We reviewed all the terms and definitions you have to know how to apply the psychrometric chart. We looked at all the terms of dry bulb, wet bulb, dew point, specific humidity, terms we need to know to apply the chart. And then we deconstructed the psychrometric chart into its elements and rebuilt it to evaluate psychrometric processes. Thank you very much for your time. Are there any questions?
There are currently no questions in the chat, but if anybody does have any, you can type them in or feel free to unmute yourself.
I have a question. You mentioned that this presentation will be available on Veritech's website. Do we need an account to access that?
Nope, I upload it all and then I will send out an email or a website link to it so you have direct access, but it's all available without logging in.
Thank you.
You're welcome.
Will you be sending the certificates to us, or will we have to go online to get those?
I will send you a link to where I have them stored in our Google Drive.
Good deal, thanks.
Yep. And then we do have one question in the chat. Forrest, I just want to make sure that he confirmed what you were asking. So Dan, you had a 97 dry bulb condition. That was because it was something that we see in Phoenix, correct? He just wanted to know if that was actual because it wasn't ASHRAE.
That is, yes, that is correct. Some of our local engineering groups use 9776 for a monsoon evaluation of their equipment selections.
Okay, yeah, Forrest, so the high latent is, we have monsoons.
In fact, we have one team that's actually using 78 degree wet bulb, 9778. I measured last August, second summer in a row, dew points in Phoenix on a monsoon day of 72 degrees outdoors.
Yeah. Any other questions? All right, nothing's coming in and we don't want to keep you guys any longer. So if you do think of any questions, feel free to email me or Dan or your salesperson here at Veritech.
Thank you very much for your time. And again, full apologies for going over today.
Thank you, Dan. And thank you everybody for joining us.
Bye. Bye-bye.
Thanks very much.
Thank you.
Thank you.
Thank you.